Good morning, students. Today let us focus on Unit 4, Fourier Series. So here, in this word itself, you can find the term series. So here, you are familiar with sequences and series, right? So what is sequence? Sequence is nothing but arrangement of numbers in which any two successive numbers have a definite rule. So if you observe this sequence, in this sequence I have written all natural numbers. So if you consider any two successive numbers, if you take first two numbers, difference between first two numbers is 1. Difference between second and third number, that is 1. Again, difference between third and fourth number is 1. So the difference between any two successive numbers is 1 here. That means this sequence is following some particular rule. This arrangement is following some particular rule. That's why this arrangement is called a sequence. Now, one more example is some 1, 4, 9, 16, 25, 36, 49, so on. Even in this sequence, if you observe, all these are squares of natural numbers. That means there is some particular rule. All these numbers, they are following a particular rule. This arrangement is also called a sequence. Now, let us come to the word series. So here, series means if you write all these numbers using one arithmetical operator, some plus, 1 plus, 2 plus, 3 plus, 4 plus, 5 plus, so on, this is a series. Okay, if I write 1 plus, 4 plus, 9 plus, 16 plus, so on, even this is a series. You are familiar with series. You studied arithmetic progression, geometric progression, harmonic progression in 11th and 12th standards. All those are nothing but series. Now, here already we are familiar with some Maclaurin series, Taylor series we studied in first semester. So what is difference between Maclaurin's? Not exactly difference. What is the need of this Fourier series? Again, already we are having Taylor series, Maclaurin series. So what is Taylor series? What is Maclaurin series? Here sequences and series. Here series may not be particularly in terms of only numbers. Even you can write variables as series. Here this is a series, algebraic series. Here we are having all x terms. Okay, so any function can be expanded in the form of algebraic series. Here you can write e power x as x power 0 by 0 factorial plus x power 1 by 1 factorial plus x square by 2 factorial plus x cube by 3 factorial plus so on. That means this is equal to 1 plus x square by 2 factorial plus x cube by 3 factorial plus so on. What is this? This is expansion of the function e power x. How do you get this expansion? You are familiar with the procedure of Taylor series. So Taylor series, using Taylor series, if you using that procedure to write for Taylor series, we get this. How? You know the general formula of Taylor series. So using that general formula, we can expand any function in the form of algebraic series. Right? So can you recall that general formula of Taylor series? If you recall that general formula, some f of x plus h or f of x equal to, what is that? Taylor series, f of x equal to f of a plus x minus a into f dash of a plus x minus a whole square upon factorial 2 into f double dash a plus so on. This is general formula of Taylor series. Using this Taylor series, we can find or we can expand any given function in the form of x terms. Okay. Now, even you are familiar with Maclaurin series. So in Taylor series, if you put a equal to 0, then you get Maclaurin's series. So Taylor series and Maclaurin series are already available. But here we are seeing one more series, Fourier series. Why? Here Taylor series and Maclaurin series, they are useful only for continuous functions. Okay, that means you can expand any function Taylor's and Maclaurin series. Here using these series we can expand only continuous functions. Continuous functions. But using Fourier series, Fourier is the name of a mathematician. Fourier series, using Fourier series we can expand continuous to expand continuous as well as discontinuous functions. Discontinuous functions. This is the advantage of Fourier series when you compare these. Here using Taylor's and Maclaurin series we can expand only continuous functions, but using Fourier series we can expand continuous as well as discontinuous functions. Now what is continuous function? So continuous function you studied in 11th standard. Mathematically if you see here some limit x tends to c f of x equal to f of c, and if you find left hand limit and right hand limit, c minus fx should be equal to c minus fx equal to limit x tends to c plus fx. If these conditions are satisfied, if you find left hand limit, if left hand limit at point C is equal to right hand limit at point C, and also value of the function at x equal to c is finite equal to f of c, then any function is said to be continuous function. Okay, discontinuous function here, and if you observe geometrically or graphically, here if graph is like this, if curve is continuous, that is called continuous function. Continuous function. So here discontinuous functions, even you studied these discontinuities in 11th standard. Here Fourier series is applicable to both continuous functions as well as discontinuous functions. So continuous function we have already seen, this is continuous function. Here discontinuous functions means there are three types of discontinuities. That means here at some point if curve is like this, or if curve is like this, jump discontinuity, that means like this. This is removable discontinuity, and this is a jump discontinuity, And one more graph is, this is infinite discontinuity. Okay, mathematically if you observe mathematically these discontinuous functions, if f of x tends to c is not equal to f of x tends to c, limit x tends to c, here limit x tends to c, fx is not equal to f of c, then this is called removable discontinuity. And if limit x tends to c minus is not equal to limit x tends to c plus fx, then it is jump discontinuity. Okay, if limit x tends to c fx equal to plus infinity or minus infinity, this is infinite discontinuity. Okay, so for any type of function, whether the function is continuous or whether function is discontinuous, then that function can be expanded using Fourier series if it satisfies certain conditions. That means here any discontinuous function, but here that function must have finite number of discontinuities. So if function has infinite discontinuities, then it cannot be expanded using Fourier series. So any function has some removable discontinuity or it has finite number of jump discontinuities, even then that function can be expanded using Fourier series. Now you may understand the advantage of Fourier series. So Fourier series is useful for any continuous and discontinuous function. But here, where are you using or where do you use these expansions in engineering or in your particular branches? Here Fourier series is useful in vibration analysis and in heat conduction problems and even in signal processing. That means there are continuous signals and some discrete signals. If you want to convert those continuous signals and discrete signals into mathematical form, we write those signals in the form of Fourier series. Okay, so here Taylor series and Maclaurin series, they look like an algebraic series, infinite algebraic series. But here Fourier series is an infinite series in terms of sine, trigonometric terms, in terms of sine and cos terms. Okay, here Fourier series, general form of Fourier series is fx equal to some a0 by 2 plus summation n equal to 1 to infinity an cos nx plus bn sin nx. This is Fourier series. That means Fourier series is in the form of cos terms and sine terms. Okay, so here to write any function or to expand any function in Fourier series, we should know the value of a0, an and bn. So here, before this expansion, fx should satisfy, I have told, it should satisfy some conditions. Then only we can expand that function in the form of Fourier series. Whether that function is continuous or discontinuous, it should satisfy some conditions. So here fx should satisfy Dirichlet's conditions. Fx should satisfy Dirichlet's conditions, then only we can expand that function in the form of Fourier series. So here, what are Dirichlet's conditions? Let us come to the point. What are Dirichlet's conditions? Here, Dirichlet's conditions means that function must be continuous or a discontinuous function, but it must have a finite value. So that function is finite, and here fx must be, Dirichlet's conditions are fx must be single valued and finite, and fx may have finite number of discontinuities fx may have finite number of maxima and minima. Finite number of maxima and minima. These are Dirichlet's conditions. That means here fx should satisfy these three conditions. If fx satisfies these three conditions, then only we can expand that function in the form of Fourier series. So what is first condition? Fx must be single valued and finite. Then fx must have finite number of discontinuities, and fx has finite number of maxima minima. So if fx is single valued and finite, and it has finite number of discontinuities, and it has finite number of maxima minima, then we can expand that function using Fourier series. So any function which satisfies these conditions can be expanded in the form of Fourier series. Okay, and here if you want to expand any function in the form of Fourier series, you should know the values of a0, an and bn. So we find a0, an, bn using Eulers formula or Eulers formula. Using Eulers formula, we can find values of a0, an and bn. Now, so how do you find a0, an, bn using Eulers formula? So what is this Eulers formula? Let us see. Here fx equal to, already we know this Fourier series. So what is that Fourier series? Fx equal to a0 by 2 plus summation n equal to 1 to infinity an cos nx plus bn sin nx, right? Now let us integrate this function both sides with respect to x under the limits some c to c plus 2 pi. Let us take general limit c to c plus 2 pi some fx dx equal to, here a0 by 2 integral c to c plus 2 pi dx plus summation n equal to 1 to infinity an integral c to c plus 2 pi cos nx dx plus bn integral c to c plus 2 pi sin nx dx. That means we are integrating this Fourier series both sides with respect to x under the limits c to c plus 2 pi. Now if you integrate these on both sides, on left hand side let it be as it is. Integral c to c plus 2 pi fx dx. On right hand side, a naught by 2, if you integrate dx, that becomes x under the limits c to c plus 2 pi. And here, within the summation n equal to 1 to infinity, this first integration is 0 plus even second integration is 0. Since integral c to c plus 2 pi sin nx dx equal to integral c to c plus 2 pi cos nx dx equal to 0. Now, if you apply limits here, this becomes a naught by 2. Here c plus 2 pi minus c. So, plus c minus c will get cancelled. You get a naught by 2 into 2 pi. You can cancel this number. Then, you get a naught. Transpose this pi to left hand side. If you transpose this pi to left hand side, we get 1 by pi integral c to c plus 2 pi fx dx equal to a naught. So, a naught can be obtained or can be derived from this Fourier series. Okay, in the same manner, we can derive an and bn using this Fourier series. So, if you derive in the same manner, we get an equal to 1 by pi integral c to c plus 2 pi fx cos nx dx and bn equal to 1 by pi integral c to c plus 2 pi fx sin nx dx. So, here a naught, an and bn can be obtained using Eulers formula. Now, after getting a naught, an, bn, that means if you use these formulae, then after simplifying these integrations or integrals, we will get some numbers or some a naught, an and a naught will be constant always. An and bn may be constants or may be in terms of n. Okay, so after getting values of a naught, an, bn, you have to replace a naught, an and bn in this Fourier series by their particular values. Then we get Fourier series. Okay, so without these derivations directly, you can write Fourier series as fx equal to a naught by 2 plus summation n equal to 1 to infinity an cos nx plus bn sin nx. This is Fourier series. Now, a naught equal to 1 by pi integral c to c plus 2 pi fx dx, an equal to this, bn equal to this. So, these are the formulae to get Fourier series. If you know any function or any function is given, then using these three formulae, first you have to obtain value of a naught, an and bn, then write this Fourier series. Again in this Fourier series, write values of a naught, an and bn to get particular Fourier series for any given function. Now, here in our unit, there are some 4 to 5 concepts on Fourier series. That means getting or expanding any function in the form of Fourier series in different intervals. That means here this unit contains different topics. They are Fourier series in the interval 0 to 2 pi, then Fourier series in the interval minus pi to pi, then Fourier series in the interval 0 to 2L, then Fourier series in the interval minus L to L. So in different intervals, we have to obtain Fourier series for any particular given function. So these intervals also will be mentioned along with the function. Now if you observe, in 0 to 2 pi, again two types, here for continuous function and for discontinuous function. For continuous function and for discontinuous function, there are two types. In the interval 0 to 2 pi, continuous and discontinuous function. Now in the interval minus pi to pi, again there are two types, continuous and discontinuous. But here again in continuous function, again you can observe three types, even function or odd function or neither even nor odd. Neither even nor odd. Again in discontinuous functions, we may find even functions, we may find odd function or neither even nor odd. Now in the interval 0 to 2L, continuous and discontinuous. Again in the same manner, just like in the interval minus pi to pi, here in the interval minus L to L, again you find continuous and discontinuous, and here even, odd and neither even nor odd, three types. Again here in discontinuous function, even, odd, neither even nor odd. Okay, and one more concept we are going to study, half range Fourier series. Half range Fourier series. In this half range Fourier series, half range sine series and half range cosine series. So these five concepts we are going to study in the interval 0 to 2 pi, minus pi to pi, in the interval 0 to 2L, and in the interval minus L to L. Last concept is half range Fourier series. Now in the next video, let us see what is discontinuous, what is continuous function and what is discontinuous function. Already we have discussed, but here how can you identify from the given question whether the function is continuous or discontinuous? Let us see in next video.